A 20 centimeter by 20 centimeter square loop lies within a uniform magnetic field as shown. The strength of the magnetic field is increased steadily from 0.5 teslas to 1.5 teslas in 20 milliseconds. What is the value of the induced current in the loop? So for this problem, this is basically an electromagnetic induction problem. And to start off, we have to find the induced current that's generated in this loop as the magnetic field varies. In order to do this, we have to find the EMF that's induced in this loop, because that induced EMF will generate a current around this loop. So to find the induced EMF, we first have to know Faraday's law, which states that the induced EMF is equal to the change in magnetic flux, or this phi b symbol, divided by the time, or the change in time, is equal to the induced EMF. So now we can think about what these different terms mean here. For this top term, this is the change in the magnetic flux, and we know that magnetic flux, or just phi b, is equal to B times A. And we can say that the change in magnetic flux in this scenario, we know that the magnetic field strength changes from 0.5 teslas to 1.5 teslas. However, the area, or this A term here, does not change at all. It's always 20 centimeters times 20 centimeters for the area of this loop. So to express the change in the magnetic flux, or delta phi b, we can write that as delta b times A. And we can also see that down below on the bottom here. If we were to put in a delta there and a delta on that side, we can just bring that right up top. So let's clear this out now. And then we can also just divide this by delta t. And we have our delta t because that's our 20 milliseconds in the original problem. That's the time value of which this change in the magnetic field occurs. So now we can plug in numbers to find our induced EMF, and that'll help us to find the induced current. So we can say that the EMF is equal to delta B. We know that the strength of the B field changes from 0.5 teslas to 1.5 teslas. So the change in the magnetic field is just 1 Tesla over this 20 millisecond period. So we can just write 1, or you can just not write that, but we'll just write it here to help out with putting in our values here so we can see what we're doing more clearly. And then we need our area, which is going to be 20 times 10 to the negative 2 squared. Just length times width here, 20 centimeters times 20 centimeters. And then we divide that by our delta t of 20 milliseconds. 20 times 10 to the negative 3, because milli is times 10 to the negative 3. And that will give us an EMF value. If we calculate this here in our calculator, see, this will give us a value of 2 volts for our EMF. Okay, so now we need to use this to calculate our induced current. And we can do that just simply by Ohm's law, which we know from circuits. And we can just make some room here, clear this out so we can write our Ohm's law relationship. So we have, for Ohm's law, we know that the EMF, or another way we can write that EMF is also just as V. If you're familiar with Ohm's law, you'll usually see it written as V. We can say EMF, the EMF and V are the same thing for this purpose. So we'll just use EMF to keep the symbols consistent. EMF will be equal to I times R, or we can write this as I, our induced current, is equal to EMF divided by R. So now we can just plug in numbers. Our induced current, I induced, is equal to the EMF, 2 volts, divided by our resistance, which I have written over here. The resistance of that resistor right there is 10 ohms. So we'll just divide by 10 ohms. And then 2 divided by 10, if you just punch that in, that's just 1/5 amps, or 0.2 amps. And that's our answer for our value of the induced current. Now, what way do we think this current flows through the square loop? Or another way to say it is, the way in the problem, what is the direction of the induced current through the resistor? So to figure this out, you have to think about Lenz's law. And Lenz's law states that the direction of the induced current will be in such a way that it opposes any change in the magnetic flux through a loop. And what's happening to magnetic flux here? We know that the magnetic field strength is increasing through this loop from 0.5 teslas to 1.5 teslas. So it's increasing, and we see from the x's in the middle of the loop that it's increasing into the page. So if we apply the right-hand rule, point your thumb into the plane of the paper, and that is the way that our flux or magnetic field strength is increasing. And so there, by Lenz's law, we have to induce a current which will create a new magnetic field that will oppose that change in magnetic flux. So we have to create a current that will make a magnetic field that goes out of the page and opposes that increase in flux that's going into the page. So now we can continue to apply our right-hand rule. Point your thumb out of the page, that's the direction of the magnetic field that we need for our induced current, and then just curl your fingers and you'll see that they curl in a counterclockwise direction, and that's the direction of our induced current. So we can draw a little arrow on our chart here, and we can say the current flows from left to right through the resistor. This is I induced. And we'll just write that down here. We can say that the current flows, we'll say it flows counterclockwise around the loop, or you can say it flows from left to right, and that's through the resistor. And there are our final answers for this problem. And that's it for this video. Thanks for watching.